before running analysis, just make sure that the structural elements that we have assigned are in the correct arrangement. So for which you can go to display option and other object assignments, and for frame assignments select section, and for cell assignment select section, apply. So we can see slab that we have the arrangement or the assignment of the element is done properly or not. Go to the elevation view, apply. So beam, column, okay. In this way you can check circular column. So this is how you will check whether the assignment of the element is done properly or not. So after doing that, we will run the analysis. Go to analyze, firstly check model. So there is no any warning messages. Then analyze, set load cases to run, make sure that it is ticked, okay, it is checked, that is calculate diaphragm center of rigidity, else it will not give the diaphragm center of rigidity, which is very important to check whether the building has eccentricity or not by comparing with the center of mass. Run now. So once it is done with the analysis, we have to check several results and compare with the code values whether those values are within the permissible range or not. So I'll start with the displacement and drift. Display, go to story response plot and maximum story displacement, select earthquake X, because we will check the displacement and drift along x-axis and y-axis for the earthquake loading. So it comes as 22.8 mm and the maximum value is, so according to the code, let me show you, story drift in any story shall not exceed 0.04 times the story height. So that means the story displacement should be within the value 0.04 times the story height. 0.004 into story height, that is 3 meter, 3 meter, 3 meter, 3 meter, that is 12 meter. So the maximum value is 48. This is 0.048 meter, that means 48 mm, and our value has come as 22.8, which is within the permissible range. So that is the story displacement along x-axis is safe or is within the permissible range. Similarly EQY, this is 18.33 mm, and the drift shall be less than 0.004. So it comes at 0.001. This is also okay, and for x-axis it is 0.0249, which is also less than 0.004. So that means story drift and story displacement is within the permissible range. So the very first check is done. Now second thing that we'll check is the model results. Okay, now let us close this window. Now go to display and in the sort table go to analysis results, and in the analysis results select structure output and go for model information and select model participating mass ratios, and at the same time you can also select center of mass and center of rigidity. I'll explain you this. Okay, so firstly model participating mass ratios, and let us go to the code first. The code says the number of modes nm to be used in the analysis for the earthquake shaking along a considered direction should be such that the sum of total model masses of those modes considered is to be at least 90% of the total seismic mass. That is the number of mode considered. So we have considered 12 number of modes, and for this 12 number of mode, the sum of the mass participating in the seismic motion should be greater than 90%, but we have 100% of mass participation, which is extremely good. But If it was not the same case, then at least at this value, that is the last mode, there should be 90% of modal, or that is mass participation. Okay, that is the simplest term I can make it clear about it. So there should be at least 90% of mass participating at the last mode. That is the concept. So this is the first check in the modal participating mass ratio, that is modal result. At least 90% of mass participation in the nth mode of vibration. If it was not, so this is by default we are provided with a 12 number of modes. For example, if it was 80% or 89% in this case, then we had to increase the number of modes till the value exceeds 90%. I will show you how we can increase the number of modes later on. So this is the first check, that is the at least 90% of mass participation at the nth mode, but for now it is 100%. That is good, as I said. The second check is normality in the time period. So this is the time period. So basically the time period was provided as 0.483 second, that is 0.075 into height of the building to the power 0.75, and that is by considering the height of the building only. If you see that the time period is provided considering the height of the building only, so that means for a height of h the time period is same, which is very conservative. That is not true. The time period of the building depends upon the loading, depends upon the material, depends upon the condition, depends upon various things, so that will be different. But with respect to 0.075 s to the power 0.75, that is a very conservative time period. So the time period given was 0.483, but the time period is 0.697. so this is by considering the loading that we have provided in the element, in the structure. So this is what I'm trying to explain, that is the time period that we provided is different than that of the time provided after the analysis. The time period provided is 0.483, but the time period, the actual time period is 0.697. so the difference between these two values for a residential building should be between 1.4 or 1.5. 0.697 divided by 0.483, so there is a value of 1.44 times, that is the value is 1.44 times greater than that we provided. So there is an exceedance of 44% in the time period. So that means we have done pretty good job with the load assigning. So basically if the value, or if the difference between time period given by Etabs and time period provided by you is less than 20%, then there should be some problem with the assigning of mass source, restraining, constraints, etc. If the value is between 20% to 40%, then it is okay. If the value provided by you and the time period provided by the Etabs ranges between 20% to 40%, then it is okay. And if it is greater than 40% and less than 60%, or we can say 50%, it is excellent. The loading has been done properly. And if the value is greater than 100%, the time period provided by you is 0.483 and the time period provided by the Etabs analysis is 1 second, then there is a mistake in concrete properties, or the sizes of element has been done, there is mistake in the sizing of the element. If it is greater than 1000%, that is infinite, then there should be the problem with the connection or interconnection of the elements. The elements have not been joined properly. So that is how we can identify the mistakes. So this is about the time period. So now we will compare the value of ux, uy and rz in order to consider the torsional discomfort in the building, and for which the value of ux and uy should be greater than rz in the first two modes, and that ensures the building undergoes translation in the first two modes along x-axis and y-axis respectively. That is, if there is translation along x-axis in the first mode, then there should occur translation along y-axis in the second mode, and which occurs when the value of ux or uy in the first mode and second mode is greater than 40% general value. If the value of ux or uy is greater than 40% in the first and second mode diagonally, you can see diagonally, then we can ensure that the building does not undergo torsion, and hence there is no torsional discomfort in the building. And as I have said, we have to compare the value of ux, uy and ux, uy and rz, and here you can see the value of ux is 0.72, value of ui in the first mode is nearly equal to 0, and this should be applicable for the second mode diagonally. That is, the value of ux in the second mode should be nearly equal to 0, and the value of uy should be greater than 40%, or we can say the value of ui should be greater than rz to ensure there is no torsional discomfort. And in the third mode, the building undergoes rotation, and for which the value of rj should be greater than ux and uy respectively. So if we see, the value of rz is 0.1346 and 0.001, so which is less than ux and uy respectively, and it is, or the value of rj should be greater in the third mode. So that means the first three modes are responsible for the torsion consideration. So here you can see in the table 6 of IS 1893 part 1 2016, the first three modes together contribute at least 65% mass participation factor in each principal plant direction. And for fundamental axis, that is the first three modes in respective plant, so you can see 72%, 85% in the second mode, as is said, 65% in the first three fundamental modes of the principal axis. Similarly in rz you have 73, so that is okay with us. So we can also uh, identify whether the buildings undergoes torsion at the first step or not, at the first mode or not, just by observing the animation under modal analysis. So run this at the in the plan view and go to deformed shape and select mode, apply. Now if it rotates about its center point, then it is then it can be said that the building suffers torsion. And if there is a translation motion along x or y, then we can understand there is no torsion in the first or second mode. So start animation. So here you can see that it is uh, translating about x-axis, so there is no torsion. Similarly in the second mode, apply, start animation, it is translating about y-axis, which is as per our consideration. And in the third mode, there should be rotation about the center point. So you can see here there is a rotation, so that means after second mode only there the building undergoes torsion or rotation. So this is how we can interpret the building from the animation mode also. This is about modal participating mass ratios. Now let us check for center of mass and center of rigidity. So according to our code, it says the center of rigidity and center of mass, the difference should lie within 5%. If it doesn't lie within the 5%, then the design eccentricity has to be taken and further analysis has to be done. For checking the eccentricity, I have already made a video which you can find out in my profile, and you can check out from there how to make a Excel sheet for it. So that is how we'll check the eccentricity. Now, so for increasing the number of modes, you have to go to, okay, unlock this and then go to define modal cases, and here modifier showcase maximum number of modes. You can put any of value, for example let me put 20, then okay, let me run this again and go to display show tables, and in structure output select modal participating mass ratios, Now here the number of modes is 20 and the model participating exceeds 90% at the nth mode. So in case if the model participation is not satisfied with the 12th mode, then you can increase the number of mode. Now we will check the concrete frame design, that is the reinforcement designing of the structure. So for which we will go to design and run concrete frame design, start design or check, or you can directly click this over here. So it will check the concrete, and this gives us the reinforcement, that is 1016, 1543, 1798. So these are the reinforcement provided, and let us check or verify all member passed, whether all the member pass or not, our design check. So all concrete member pass the design check, so our structure is safe, that is all concrete member passed the design checks. Now you can design for beam column capacity ratio. So basically from Etabs considering Etabs 2018, it takes beam column capacity as 1.4. Previously in Etabs 16 it took it as 1.1. that is why the reinforcement comes slightly greater in Etabs 18 than that of Etabs version 16. So you can turn it off, that is you can design beam column capacity, you can do it no, and you will see that the reinforcement will reduce. So it is 1016, 1543. Now let us do concrete check once again, 1543. Now it comes at 831. So this is how the reinforcement will reduce, as it will reduce the beam column capacity. So for now I will consider beam column capacity design yes. Okay, and display design info. So this is the longitudinal reinforcement for the beam column. Similarly you can do it for rebar percentage, it will show you the rebar percentage. For column the rebar percentage should not exceed more than 4%. Exceptional value is 6%, but generally it should be kept low than 2.5%. Similarly beam column capacity ratios, it should be less than 1.4 beam column capacity, and for column beam capacity it should be greater than 1.4. So you can see that for the design the Etabs has reinforced, or the reinforcement that it has designed gives the value greater than 1.4. Identify shear failures. So for now let me go to longitudinal reinforcement and go to the elevation view, apply. So let us see the maximum reinforcement to be provided: 2481, 2480, 1964, 2886. So you can see here that the reinforcement is coming greater at the topmost story than the bottom story. So it has 1462, it has 1772. So this is generally due to the moment being more at the topmost floor than at the lower floor. So I found the maximum value of reinforcement as 2487. Okay, 2487. So now let us provide reinforcement as 2487. Go to section properties, frame section, and for the circular column modify show rebar. And okay, as I said, if we change this value then there will be some differences or some changes in the reinforcement. Okay, so clear confinement 40, number of longitudinal bar 3, and keeping this as longitudinal bar 12 and this as 16, this as 8. Okay, so this is the minimum or standard requirement of reinforcement in a column for a size of 300 by 300. So let us see how much change there will be in the reinforcement. Run analysis from here. So we had 2487 in this elevation view C. Okay, so let us see how much reduction. 2187. So there is a significant reduction in the reinforcement provided by the Etabs. So the maximum value now is 2239 for the reinforcement area of 2239 mm square. The area of 20 mm bar is 314. So for this we have to provide 8 number of 620 mm bar. So it will be 314. So 2512. Let us unlock and go to define section properties, frame section, modify, column, modify story bar, and we'll provide 20 mm bar, 20 mm bar. Okay, and keeping this as reinforcement to be checked. Okay, now let us run this again and check whether the reinforcement provided by us will be sufficient or not. So if the color is red, then it is overstressed. So for now it is not overstressed, so that means verify all member passed. Okay, go to 3D view, and I don't think there is red color anywhere, and go to display design info and identify all failures. So there is no any failures with the reinforcement that we have provided, although it is expensive because we cannot provide 20 mm bar for all the column because it was not needed for every column. Just I wanted to show you. Now let us provide a less reinforcement area, then you will get the idea what I'm trying to say. So go to section properties, frame section, and modify or show reverse reinforcement to be checked. Let us provide 16 mm bar in this, and okay. Now run. Go through the concrete frame design. Now you see there is a red color over here, so that means over stress. You can clearly find this. Verify all member will be passed, but while uh, through the display design info you can clearly find out the failures. So you can see that beam column capacity failure, that is it is being overstressed. If you right click over here, then you will see overstressed written here. So this is how you will check for the reinforcement. And if you want to design reinforcement manually, or if you want to design for respective columns, then what you can do is just go for the reinforcement to be designed. So go to section properties, frame section, and modify show property. Keep this as reinforcement to be designed, and okay. And again run this, and concrete frame design, and go to the elevation view. For example, if I have to design column for this, if I have to design column this one, then just right click on the column and it will come, and this window will pop up, and then go for details. Now you will see you have the summary report of the column, that is the level ground floor, column element, unique name, section ID, and the combination ID for which the column has given the maximum reinforcement, that is decon 11, and this comprises of 0.9 dead load plus 1.5 times of earthquake in x direction, and this is the length of the column, or that is the height of the column, width, cover, and this is the river area, and this is the design moment, and for this design moment the river area has been provided this river percentage, shear reinforcement, similarly BCR detail, that is beam column capacity ratio. So this is the BCCR details. Envelope, that is envelope means comprising of all the loading condition. Beam column capacity ratio 1.6 and 1.4, as I said, 2018 version Etabs considers beam column capacity as 1.4. You can also export this to Word documents like this by saving this as your specified name. So this is how we'll design column or interpret the result of column. Similarly for beam, this is the uh, reinforcement at bottom, reinforcement at top, this is for the middle, this is for the extreme left, this is for the extreme right, and again you can see for details, and flexural moment, flexural reinforcement for moment. So this is how we will interpret the concrete beam and concrete column data from Etabs. Slab will be we can design slab manually. We can also find the base reactions for the design of footing, and for which we have to define a new load combination. Basically footing is designed for uh, dead load and live load only without any scale factor. So decon 2, this is 1.5 times of dead load plus live load. So add a copy of this and provide scale factor as 1 1 1 1 1 1 1 1 1. Okay, so run the so the analysis is done. Go to plan at the base, select base, and go to this display support or spring reaction, or you can even go to display, and then you have force stress diagram, support, spring, decon 2, and we will design footing for vertical force and moment along x and y, tabulated, apply. So this is the moment, force for which the footing will be designed respectively. So this is how we will consider the size of consider the footing forces or the column forces required for footing design. Also the different stress diagram can be viewed. Okay, so go to display frame link forces, or you can even go here and force stress diagram, frame link forces, and whatever you want to find. For example, decon 1, and I have to find out axial force diagram. So generally the axial force is or decreases with the story level, and shear force along 2 direction, and moment along 3 direction. Okay, so this is how the stress diagram is interpreted in Etabs. Then okay, summary report. You can print out or create report by showing show project report, and it will show you all the details. So it is analyzing results. Wait for some time. So this is the summary report. Okay, you can export to Word document. Center of mass, center of rigidity, mass source defined, frame assignments. This is the load patterns. This is the base shear. Okay, story 1, base shear elevation, weight of the building, base shear, the uh, time period we provided as 0.483, response reduction factor 5, SAYG, this is spectral acceleration coefficient, story drapes, and so this is how we prepare a structural report from Etabs. This is the end of the video. I hope it was helpful to you.